Hi, this is Mahalakshmi. Today I'm presenting Shapley Value-based Satellite Communication Bandwidth Allocation Strategy. Satellite communication is popularly known as SATCOM. Bandwidth and connectivity are two main expensive resources in SATCOM. When the user requires more bandwidth and connectivity, a request is raised with the service providers to increase the internet data, which in return open the ticket with the remote terminals. Remote terminals communicate with the satellite system controller, and the satellite system controller allocates the resources based on the terminal needs. Here is the typical SATCOM design that replicates this discussed scenario. Our motive here is an implementation of an effective technique to help the SATCOM network operation centers to distribute the resources fairly and effectively. I would like to address this issue in two steps. For the first step, we implemented our model using the loss of control theory. Linear quadratic regulator controllers were developed at the terminal level to determine the bandwidth requests. For the second step, we implemented the Shapley value-based cooperative game theory techniques at the satellite system controller to process the bandwidth requests. For example, the satellite system controller is like a money manager over here, and the people over here are like the remote terminals. Money managers distribute the available budget dynamically based on the needs of the people. In the same way, satellite system controllers will distribute the available resources to the remote terminals. The Shapley value also identifies a socially fair, good quality allocation for all remote terminals. Here, the competitors work in the direction of winning by forming coalitions. In this game, the individual fairness is guaranteed. For each player, it is optimal, and the average fairness of the complete system is also high. The social optimality property ensures that each player in the game receives the best utility for the individual and to the complete system. We were able to produce the results successfully using these two techniques. This figure indicates that using LQR techniques, that we can able to dynamically determine the requested data rates of 4 different remote terminals. The x-axis represents the time, and the y-axis represents the requested data rates. And this figure over here shows that we are able to successfully distribute the bandwidth resources to 4 different remote terminals. The blue lines over here represents the requested data rates, and the yellow lines represents the distribution. Our future goal is to compare these results with different allocation strategies. Thank you.